Hey everybody, welcome to the Pipeline Integrity Show. I'm your host Hussain Fadhel. We just finished off a wonderful interview with Ian Smith where we discussed defect assessment and program development. Hope you enjoy the interview and see you soon. We have our honorable guest on today, Ian Smith. Welcome to the show.
Thank you, Hussain.
So Ian, we are starting our Titans of Industry series on the Pipeline Integrity Show. You're our inaugural guest, and in the off chance someone doesn't know who you are, could you please give us a nice introduction?
Well, thanks. Honored to be here, and hopefully we can have an interesting show. So I got my first job as a data analyst working for a company called Piptronics. And at that time, data analysis was a lot more laid back, no qualification rules. I walked into the job on the first day, I was all excited, and my boss said to me, "Ian, can you build a table?" I'm like, "All right." That was back in the day when we were glad to have any Microsoft Office on a resume and the chance to prove that it was real. They said, "No, we just moved over from the other side. Can you put together this table?" It was a physical table. But I got the job because I was an engineer, and they hired me and one other engineer. And so I say we were the first pipeline integrity data analyst engineer. So that was 1996, kind of a picture on how far the industry's changed. And so I did that for 3 or 4 years. And that company was Piptronics was bought out, so I moved to a job with a liquid operator, Sun Canadian Pipeline, so my Ontario roots, and that was a small company running liquid refined product, and we had 2 engineers, and so we got to do everything. See, the pipeline integrity program was just about 10% of my job. So, and I was the pipeline integrity engineer. So again, another picture on how much things have changed. Process all kind of runs the same, but there was a lot less complexity then. And that line was very clean. So that was a little bit of the reason as well. But certainly things were a lot cheaper and easier back then. So I worked through all the different engineering positions there, or engineering position where you got to see everything, and I left there in about 2010. And when I left, I was the manager of engineering and maintenance, and I worked on my own for a couple of years doing contracting, and then moved to a company called Quest Integrity, who had a ultrasonic inspection tool, and we're adapting that from the heater world into what was a new market for the industry, the unpickable. So I worked with them, helped them sort of convert their reports and the reporting and their methodologies from the heater world into the pipeline world, and also did a lot of engineering assessment, fitness for service work, and got to do some product development there. I was there till 2016, and then I've been on my own for the last 4 years doing pipeline integrity consulting with my company, ID Smith Pipeline Engineering, and providing just a wide array of integrity services, and as an independent consultant.
Well, thank you, Ian. I want to say you're being a bit humble. I know you also do the Clarion training, which I have attended before, and I recommend everyone, if you haven't been to Clarion, go to their website. I can put in the link below, and definitely attend Ian Smith's class, because it was extremely informative. I believe it's a defect assessment workshop, correct?
Yeah, the pipeline defect assessment workshop. Yeah,
perfect. So I'll just put in my 2 cents. I had the opportunity to work with Ian Smith in the year approximately 2017. It's like a walking reference library. So any question I had, I was able to ask Ian, and I'm sure at the end of the show, when we share your contact information, if anybody wants to reach out to Ian, I'll put in the description below. So Ian, again, thank you for coming on the show. Let's jump right into it. I know your strength, your background, like you were describing, is in sort of defect assessment, ILI. So again, we have a wide range of viewers here, and why don't we start off simple? Can you just walk us through, you hear the phrase defect assessment a lot in the industry. I think for different people, it means different things and people understand it in different ways, but can you just give us the 101 on what do we mean by defect assessment and the different assessment methods?
Yeah, and it's funny, each word is loaded. So let's go, we got two words, let's break them down one at a time. First word is defect. And other words that get used are anomaly, flaw, defect. Each has a slightly different meaning, but it's an anomaly is maybe the easiest to define. It's an imperfection in the pipe. Defect is applying that it's somehow injurious. And then assessment is, how bad is it? Which is, then the fun comes in, and do the assessment, and then we have to figure out whether we're going to take an action or monitor or re-inspect. So defect assessment at its sort of heart is finding, getting an anomaly with some dimensions and deciding how bad it is. That sometimes is the easy part. The harder part is all the things around that, gathering the data, getting a spreadsheet maybe with thousands or millions of anomalies in it, and then verifying the information to see whether the assessment you made is correct or not. So at its heart, the defect assessment is putting some equations and some fitness for service approaches to something you found in your pipe. But the maybe the more interesting part of it all is gathering the data and the context around it and decision making. Do you dig to something? Do you repair it? Do you leave it? Do you re-inspect it? How long until you re-inspect it? That's maybe where a lot of the the interesting parts of the pipeline integrity world are.
Right. So maybe if you could, I know there's also the word that's thrown around, like you're saying, is fitness for service. Sometimes we like to use the word, though it's something different. I'm sure we can get into it. Is engineering assessment. I guess defect assessment, if you agree with me or correct me, but is maybe specific to the defect, and then engineering assessments and fitness for service assessments maybe are a bit more encompassing for asset type, correct?
Yeah, that's kind of the long and the short of it. And I think one of the confusion comes around, defect assessment can mean a lot of different things, and it tends to be, what is my spreadsheet or my software telling me the answer is in terms of the pressure or the remaining life of an anomaly. Engineering assessment or fitness for service, those will have very specific definitions because they'll come from a code. So one of the most common fitness for service codes will be API 579, and that gives you a long and detailed methodology to do a fitness for service assessment. Engineering assessment in Canada is governed by the Canadian codes, and they will give you a very specific methodology that tells you what is required in a good engineering assessment. So those have some very specific definitions. And where they tend to be used is we run an assessment, and then if it's in some kind of gray zone where we're not sure what to do with it, we may run an engineering assessment or fitness for service to get a more comprehensive understanding that may consider a bunch of factors that aren't, say, a B31G metal loss assessment that is being done by our vendors or through our spreadsheets.
Perfect. So can you walk us through, I know in industry we like to talk about the nine threats. And I remember when I was first hired, it was almost like a memorizing thing. They would stop you in the hallway and say, what are the 9 threats? So there's 9, and I'm sure we can go through them. But I think the fun ones that we often talk about are, I guess, what we call time-dependent threats. So that would be, internal corrosion, external corrosion, cracking, those kinds of things. Can you talk a little bit about damage mechanisms and perhaps what equations or methods we use to evaluate them?
Mm-hmm. So probably the first one to talk about and the most common is metal loss. And the industry sort of uses that common term, and metal loss can mean a lot of things. At its heart, we're really talking about corrosion. Not every metal loss we're worried about is. So it's corrosion, and then that can quickly be put into two different categories: external corrosion and internal corrosion, which obviously have much different drivers or causes to those damage mechanisms. But at its heart, when we're assessing it, one of the nice things about metal loss is we can assess internal corrosion, external corrosion, even some of the manufacturing metal loss, which might be, a mill defect or some imperfection in the pipe that doesn't have an active driver mechanism like internal or external corrosion. All of those can be assessed using an equation. The most common one is the ASME modified B31G equation. And basically all it's looking for the inputs is the amount of missing metal loss. So that would be, at its simplest, the length and the depth of a metal loss anomaly, and then the strength of the pipe. So we use the SMICE, or the specified minimum yield strength. And with that, those couple relatively simple properties, we're able to calculate what the burst pressure or the safe operating pressure for an anomaly is. And those equations have been around for a while. They've had some modifications, but they're actually pretty stable and pretty effective and relatively easy to use. Sometimes finding out the corrosion mechanism, that can be difficult. There's some interaction, of course, there's some other things, but at its heart, the assessment of metal loss is actually, in most cases, relatively straightforward. One of the interesting things about pipelines is, they have the main load is from internal pressure, and because of, if a pipeline is buried, doesn't have a lot of temperature stress, doesn't have a lot of other stresses on it, then the assessment really only has to take care of the load from internal pressure, and that makes our job a lot easier. One of the things that can sometimes grab us is if there is another load, say due to pipe movement or strain, then our equation isn't quite as effective. But most of the time, the sort of the B31G or that family of equation is actually quite effective.
Yeah, I just want to quickly ask, I know you used to talk to me a lot about, I used to be concerned about circumferential factors and stresses, and I remember you used to talk to me about Poisson's ratio, and that the pipe is more wants to rip open at the seam,
Yeah.
at the belly, rather than elongate or compress. Can you talk to us a little bit about that?
Sure. So buried pipe is constrained, and that means that it really can not move in the longitudinal direction. It's very fixed. So it's almost like if you roll up a piece of paper, it really wants to open up, and so that means that the more important stresses are the ones that are the hoop stress, and they want to open up that pipe. In a rupture, they want to open into a fish mouth. So I always like that image of if you come across a failure, or hopefully maybe it'll be a burst test you're doing in the lab and it fails, it will open up into a fish mouth if it's a rupture. So Poisson's ratio is 30%, and that's saying that the longitudinal stresses are only 30% of that hoop stress. And so that's why it's not impossible to have failures on circumferential corrosion, so corrosion that goes around the pipe in a ring, but it's far more likely, the far more common and dangerous situation is corrosion that has longitudinal extent. So the equations, in fact, they don't even consider the circumferential extent of corrosion, other than interacting anomalies to see if things that are close together are cumulatively adding length because metal loss features are in close proximity.
Yeah, so is there any practical difference between assessing internal versus external corrosion?
In the assessment itself, there isn't any difference at all. In fact, you don't even consider. I mean, once in a while you come across where there's internal and external happening at the same time, in which case your equation may have some difficulties in handling it. but you just would really need to account for the missing metal on both sides of the pipe. Damage mechanisms and how you address it, because sometimes external corrosion is easier to deal with. So if you have external corrosion, you do a dig, you recoat it, isolate the pipe from the corrosive and external environment, then that really doesn't have the corrosion doesn't have the ability to keep growing. Internal corrosion can sometimes be harder to deal with in terms of have we addressed the cause of the corrosion, but the actual assessment itself would be identical.
Yeah, and then one of the things that I noticed people having difficulty with is when we're doing some defect assessment and the question comes up, will it be a leak, will it be a rupture? So the failure mode. Can you talk to us a little bit about how to, I know there's a calculation for that, but just sort of how to approach that?
Yeah, so this is one, when I teach the course, sometimes the joke is that I should wear a t-shirt underneath it that says it depends, because I use that answer so many times. So basically, if corrosion is short, then it tends to, so we can call maybe 3 different modes of failure. Let's just back up a little bit and say, how can something fail? So corrosion can corrode all the way through the pipe before it ruptures. In that case, we would always have a leak. And so if the stress is low enough that the pipe is still stable, say at a external corrosion pit or internal corrosion pit, then we would expect something to leak before it ruptures. And then if something has enough stress, it can fail at 90% wall thickness. It could fail at 20% wall thickness, depending on the length of the corrosion and the strength of the wall and the stress levels. But then we can have a rupture. So that rupture could be this fish mouth that opens up, and then you'd have, and then gas line that rupture can propagate, and then you'd have a large spill volume or length of pipe affected, or that rupture can also be short and relatively stable, so that rupture doesn't keep propagating. So the confusing part is that short rupture really behaves the same way a leak does. Now, what matters is, are you a liquid line or a gas line? So there's some cases on a liquid line where if you have a small leak that's below the leak detection threshold, that leak can go unnoticed for a long period of time, and you can have a large spill volume. So we can kind of simplify this, at least on a liquid line, to say the larger the spill volume is, the worse a leak is. So a rupture can be easier to find because you not only do you have a large change in volume, you also will have a pressure drop. Some of these smaller leaks you don't. So in general, I'm not a huge risk modeling guy, but in terms of understanding the different impacts of leak versus rupture, in terms of the impact of it, that can matter. Now and then gas line would be different again, where you have a different set of hazards between a small gas leak and a large gas leak, where there's probably no doubt that a large gas leak is worse, especially as you have the chance of a ignition of the source.
Yeah, I would say one of my experiences that I can share as well is, I remember when I was working for a gas operator, one of the ways we would sort of discover small leaks is because of the frozen soil around the pipeline, because of the Joule-Thomson effect. So because there'd also be water, let's say if it was in like a wet area, so we would do an excavation, and all of a sudden, it would be quite a ways away from the pipe, but the excavator or the swamper would hit like something very hard and solid, and it turned out to be a large block of frozen soil because of the Joule-Thomson effect, and it would just freeze. And the amazing thing is that I guess the earth would freeze enough to plug the leak. So even on leak detection, it wasn't being detected because the frozen ground, it froze enough that it would plug the leak. So that's one of the ways that you're in an active leak site, you're digging and you hit ice. You have a frost plug basically.
Yeah, with the liquid line, sometimes a small leak can just show up as like a little wet pocket on the ground because the leak is going down, not up. And so you may see very little at the surface. So yeah, it manifests a lot of different ways.
Yeah. So can you talk to us some more about cracks and crack likes and the difference between those two terms? I know they're thrown around very, synonymously, but there
Yeah.
is a difference between the two. And then if you can talk to us about assessment methods and failure and damage failure modes as well.
Yeah, sure. I originally thought that crack-like was just a euphemism because crack is hard to detect and assess with an ILI tool, and especially when they started, it was very, very, very difficult. So I always thought it was a euphemism. The pipeline industry was trying to sort of guard their CYA, right? You can put a little flash up on what that stands for. What the difference between a metal loss and a crack is that a crack or crack-like has a sharp tip to it. So that causes stress to concentrate at the tip, and so a crack for a given dimension is worse than metal loss because metal loss is blunt and a crack is sharp, and so that sharp is a stress concentrator. And you'll hear that term stress concentrator thrown around sometimes. And so a crack-like, to somewhat simplify, is really just a lack of fusion or some other metallurgical flaw that comes out of the mill, and so it's in the shape of a crack, but it isn't a true crack. So what's a true crack? Well, a fatigue crack. So if I always go back to the pop can. And you work a pop can, and pretty soon you get the folds, and then cracks will show in that. Well, that's a fatigue crack, and you can imagine how that's very sharp. Lack of fusion, where or some other welding anomaly, maybe that's sharp. It's probably somewhere in between a metal loss and a crack. But in terms of assessments, we really can only assess things as if they're sharp or they're blunt. So crack-like, for all intents and purposes, we deal with it like a crack. So for assessment, while something's crack-like, it probably isn't growing. So it's our original manufacturing anomaly. But what happens over time is there's enough pressure cycles in the pipeline, and obviously a gas line where pumps are turned on and off, and the liquid transmits the pressure more directly, are more prone for the crack-like anomalies to have fatigue cracks form on them, and then they switch from a crack-like to a crack flaw. So often a crack at a long weld seam, maybe a fatigue crack on top of a lack of fusion or some crack-like. So in terms of assessing, it sometimes is helpful just to think of them all as cracks, because if you try to talk yourself into a crack-like isn't as bad as a crack, to know you're safe, you really need to prove that there's no fatigue crack on that, and there's no real way of doing that without digging something. So that's kind of what we have in our lines. The most common form of cracking, short of SCC, stress corrosion cracking, is that we have an initial stress concentrator, like a crack-like, and then a crack will form on that over time. And then that crack, fatigue crack, is much sharper and concentrates stress more, so that's going to drop our burst pressure. So we assess something using a fracture model. Some examples are API 579, log secant, Corlas. The PRCI MAT8 is the newest one that Dr. Ted Anderson developed under PRCI funding recently. And what they are is they work similar to the metal loss modified B31G, but they're working on cracks. And cracks are much more complex. We have to account for all that stress concentration, the behavior of the metal. So we have to consider both the toughness and the strength. So where material is brittle, we could have a toughness controlled failure, and where material is more ductile, we could have a strength controlled failure. So our crack assessment model needs to be able to handle the two and know which of those two regimes is relevant. And then we're worrying about our two properties, strength and toughness. And where strength is relatively even along the pipelines, toughness can vary a fair bit. And we generally don't have a great reading of toughness, especially the toughness may be lower in the seam weld where we have these crack-like anomalies. So there's a lot more, so the assessment is more complex, and getting the material properties is harder. So the general approach on crack assessment, or what I coach, is we need to put some conservative numbers in there and do conservative assessments, which means that a lot of cracks are going to fail. And that forces you to go out and dig them and get a better understanding. So there's often a lot of pain involved with starting a crack program, and it's to do with the difficulties in assessing them, on top of finding and sizing cracks with ILI inline inspection tools is difficult. And the typical error bands are plus or minus 20%. And if you think about what plus or minus 20% is, well, that's a band 40% wide. So that's almost half the thickness of the pipe is your plus or minus 80% of the time. Other 20%, it would be outside of that band. So there's just, there's a lot of sort of factors that make the assessment hard, and the general approach is to be conservative, or at least start conservative, build your program, find some anomalies, maybe do some burst tests, maybe do some material testing to get a better understanding of what's actually going on in your line. And then you can tune your assessment based upon that knowledge you gain on your line. I'm a big believer in that approach, even for metal loss, is you really need to, over time, build up this database of knowledge around your line, whether it's material properties or whether it's the type of anomalies you have or the type of causes. You'd think after a while all pipelines are the same, and I've always found that from the second line I looked at to the 100th or the 1000th or whatever I'm up to, each one is different. And operator, that's a really important role of the operator, is getting to know their line and maintaining and slowly building that database of knowledge. I think that's one of the real things that as you work at a company or work for a company now as a consultant, is to get that database and get that of knowledge and get it put somewhere. I used to have a wall of fame. Every time we had a failure or a cutout, I'd put it on top of a locker that was in my office. And there was some stuff when I came, and there's more when I was left, and hopefully there's even more now, as we're all links in the chain of building up that knowledge that helps us to operate each pipeline safely, because they can be a challenge.
Yeah, so thank you for that. I could spring off to about 1,000 different questions, so many deep topics, but let's talk about one more defect type that I feel a lot of integrity engineers will look at and feel uneasy and not really know what to do, and that's the famous dents, and especially dents, interacting dents. So plain dents, I know in Canada, for our Canadian viewers, we like to go to CSA Z662. We look over at the L over D ratio, less or greater than 20, and we kind of make our decision very quickly. But I think with the new codes and looking at cost effectiveness, and it's not maybe cost effective to go for all these digs. So we're getting more sophisticated, and we're getting into looking at doing further assessments on dents. So can you talk to us about dent assessment, and of course the most exciting part, interacting features with dents, especially stress risers, so crack-like or crack features?
Yeah, dents are by far my favorite, because in terms of assessing, you can do the most work with them. They're the hardest to start with, but they have, in terms of sort of what makes sense to put effort into advanced assessments, tends to be dents.
I have a special guest to have in mind. I know you know who I'm thinking about, but I would like to get her on one day. But yes, please continue.
Yeah. So a dent is interesting because it doesn't really fail because of pressure. So a way of thinking of that is if you're doing a hydro test on your line, you know, to destructively find and remove metal loss and cracks that may be injurious, you're not doing the same for cracks. So for dents. So what happens with dents is over time, they can fatigue and cracks will form on them. So a dent is similar to a crack-like anomaly. It doesn't behave like it, but it's similar to it in the sense of it concentrates some stress, and the pipeline cycles over time may cause cracks to form, the cracks grow, and then we'll have a failure on a dent due to a crack at a dent. So that's kind of the basics on the life cycle, which always makes me wonder, well, I mean, one, they're hard to assess, but two, when you go out in the field, you know, and we did this, I think people are moving off this lesson is getting out there, but it's a really important lesson. And you go and your ILI tells you you have a 6.1% dent and deep dent, and in your assessment criteria is anything greater than 6%, you go and inspect, and you go out there and you look at it and you go, okay, well, there was the ILI tools, you know, the caliper geometry tools tend to be more accurate for dents than they are even for metal loss besides cracking. And so you look at it and you go, okay, well, there's a 6.1% dent. What do I need to do with it? And for a lot of times, for a lot of history, and some people are still doing this, they would just look at it, say there's no cracking or anything, and then backfill it. Well, that dent could be 5 years away from the end of its life cycle, and this happened to one major U.S. operator, and they had a bunch of failures on dents that they dug. They're like 3% deep, and they'd recoated them. It's like such a shame, right? It was just the industry didn't think that way, that dent is a little bit of a ticking time bomb. So basically, what is important with a dent is how much stress concentration there is. And you talked about the L/D ratio, and that's the length of the dent divided out by the depth. And that's getting to what I think is defined as sharpness. So how sharp is the dent? And so the amount of sharpness, other ways of getting to that are strain, and are telling us how much stress concentration there is, so a dent isn't bad necessarily because it's deep. It's bad because it's sharp. So really we want to go through and find all our sharp dents. So that tells us what the severity of the dent. Another way of saying this, because it's important, the severity of a dent is not defined by its depth. It's defined by how sharp it is. There is a correlation. A deep dent is more likely to be sharp. So that's why the industry used depth for a long time. So then to do an assessment, really it's a fatigue assessment. An effective way of doing it, there's some other ones, but as you make an FEA model out of that ILI data and figure out how much pressure cycling there is, and then do that assessment to come up with a fatigue life. There's some that's sort of, we'll call that a level 3 assessment in the fitness for service world. Level 1 being simple, level 2 being advanced, level 3 being sort of the expert analysis. Well, that's a level 3. There are some level 2 tools out there that are giving us an estimation on fatigue life. So then once you've done your fatigue life assessment, then you can put together your dig program. So that's sort of the advanced way of doing it. The engineering critical analysis that would meet that definition, and there are a bunch of level 2 tools that can be used to prioritize dents. A good way to start is to have a bunch of screening criteria. Top of the pipe, bottom of the pipe, depth, is it at a weld, and to identify some dents that may be of immediate concern. A lot of older pipelines have quite a large population of dents, and you can use those criteria and those screening tools to pull together a list of what are the most severe ones, and then do some advanced level 3 assessment and see what the fatigue life is of them. So that's that's the approach I prefer, because you really are able to funnel them and find out which are the worst dents, do some FEA remaining life assessments on the worst ones, and then that will give you a scale to know whether you have to do, whether none of them are expected to fail, or whether, you have an imminent issue. The number isn't 100% real, but it's pretty reasonable. I just finished doing one, and it was a line that's a gathering line, so it didn't have a lot of pressure cycling. And once I know it doesn't have a lot of pressure cycling, well, let's do an engineering analysis. These are all meeting, this is an American line, so it's meeting the PHMSA prescriptive dent criteria, and so they had a large number of dents on larger than 6 on the top side of the pipe, dents with metal loss, but they really didn't have enough pressure cycles to drive them. So I did it, and they all passed, except for there's one dent that was larger than 6%, and somebody put a patch repair on it, back in the day, and that patch is not an approved repair on a dent. That dent, when you pretended the patch wasn't there, it passed with flying colors. Once the dent's there, or once the patch is there, and who knows what it's doing to the stress field and the residual stress from the weld, and there's no welding procedures. So that's the one they have to go repair, because of, what was well-intentioned, but people who didn't understand the dent mechanisms, which was, most people back, certainly in the 90s and well into the 20s.
One day we're going to have a pipeline repair horror show episode where we maybe get a guest on that shows or talks about all the nonsense that we've seen out there. I'm sure all well-intentioned at the time, but yeah. So let's segue into program development. So we talked about these different types of defects, and I know there's a lot more. There's one thing that's come up a lot nowadays is geotech, so pipe movement, and how to use IMU to sort of maybe track that. But let's get into program development and say, okay, let's say I'm a fresh new engineer, Ian, and I get an ILI in. Can you walk us through the development steps on how to take an ILI and then develop it into a dig program?
Sure. First thing I like to do when I get an ILI result in, you can look for the things that, where they've done a pressure or depth assessment, where the pressure and depth, are either greater than 80 or 70, whatever your depth criteria is. And if the reduced pressure is less than your MAOP or MOP, then you need to deal with that immediately. So that's kind of the first screening criteria out. That's probably highlighted right in the report.
Just a quick interjection. Can you just explain to us what you mean by MAOP or MOP and how that affects the assessment?
Sure. The MOP stands for maximum operating pressure. MAOP, maximum allowable operating pressure. They're exactly the same idea, different definitions on. So they're on which term you're supposed to use, but they mean the exact same thing. I don't know why we don't have one term on that. I should find out the history. I've asked somebody and find out the history on that. There's probably some ridiculous story around that. If when you run a pressure assessment on metal loss would be the most common one. If the safe operating pressure, so the pressure we expect only to burst at, times the safety factor is less than the MAOP, it's not deemed safe. Because we're dealing with the safe operating pressure with the safety factor, it doesn't actually mean we expect it to blow up tomorrow. We need to deal with it that way because it doesn't meet the design approach of the line, which includes everything you design with the safety factor. If that metal loss doesn't have the appropriate safety factor, you need to go after it immediately. And that's a great rule. Never need to doubt that. So that's kind of step one. Is that, and then so I find a good place to start is compare the results from this inspection to the last one. And so there's kind of two things that can go on between runs, right? First is things can grow and get worse, or new anomalies can happen. So, that's what we're worried about. That's why we inspect with our 3, 5, 7, whatever our inspection interval is. It's to guard for new and things getting larger. The thing that makes it interesting is you may even have tried to run the exact same tool, so results would be as apples to apples as possible, but it's always an apple and an orange. Never, they can be a little closer, but there's always differences between runs because inspection tools have measurement error, and that's could be causing the differences in the runs. But day one, if it's bad news, you assume it's that something has grown in the field and deal with it accordingly. If it's good news and things have shrunk, well, let's just assume that's measurement error, but we'll still at some point need to prove it. So so comparing the two
that self-healing corrosion, right?
Self-healing corrosion, yeah, it's there's a lot of that out there. Metal losses plus or minus, most ILI tools are plus or minus 10%. So if something heals 10% or if something heals 20%, both tools could have been in criteria, and be called as accurate. So it is something you're going to deal with on an anomaly to anomaly basis. So you compare the two, get a sense of whether things are a lot worse or not. Some of that's telling you how much work you're going to have to do, whether you're going to go to your boss and say, I got a doozy on my hands, or and we're going to need more time and probably more resources, or whether you can just sort of get down to work. So another step is then you take it and you compare it against, hopefully you have a set of criteria in terms of what anomalies your company believes you should be repairing to stay within your risk levels. So that won't be metal loss right up to a leak, and it won't be corrosion right up to the MOP. There'll be some. So we can generate a list off of that. And then with every run, you're going to have a dig program because you need to verify the tool, unless it's really clean, in which case you're lucky. So we're going to, when you start to pull together your dig program, there's two things you want to get out of this, right? Is to find and deal with the anomalies that are severe, and to get an understanding of how well the tool, how accurate was a tool. So did it find things? Did it classify them correctly? And were the depth measurements and length measurements accurate? So we know we're going to do some digs, and now it's a matter of, okay, what are my issues? Do I know what damage mechanisms are on this pipeline? Let's focus in on them. An example would be if we're in an AC corridor and we're worried about AC corrosion, then let's, once we go through and do our first checks, let's go see what's happening there. If our corrosion, if our shrink sleeves around the girth welds are starting to break down, let's look at all the corrosion that's close to the girth welds and see if there's a pattern there. So it's starting to look for patterns to see if we can understand what is active on the pipeline, so that we're not staring at a list of 10,000 anomalies. Some people are staring at a list of 1 million. Some people are just 100, and they can sort of break into it. One helpful thing is looking at comments. I always advise people to encourage their ILI vendors and their data analysts to put lots of comments on the anomalies. They sometimes get a little gun shy because it's hard to be really consistent, and it's hard to know if they're telling you something that, as a assessment engineer, that you care about. But I always say the more the better, and you can sort of work through those. I actually like doing a line by line comparison to the old stuff to see where there's differences in measurement. I think that really will point out what could be different. If there's something unexplained, look at the ILI data. Either go to the vendor or third parties to do a comparison to see whether changes in depth show up in the data. So if we see a big change in, if we see this change of 20% depth of metal loss, we could, you could talk yourself into saying, well, they're both, it's just the edge of the specs of the tool, so we don't need to worry about it. A much better approach is look at the ILI data, and even between different vendors, you will see a signal change if there's definite growth. So that helps you to find the areas that are potentially significant, because the way I always looked at it is you lobby for as many digs you can. That's your working with management or upper management, however that's, and then it's your job to see how much value you can get out of that dig program, right? So again, my idea of you're trying to build up the database over time, and you're trying to evaluate the effectiveness of the run, and all while trying to get the worst anomalies.
Yeah, thanks for that, Ian. You mentioned a really good point. I think especially in our industry today, COVID, the price of oil, all those things, we're under ever increasing pressure, and fairly so. Of course, if you can run it, of course, safely and profitably, then there's no point of any business. So that's fair. But I think I'm sure you hear it. I definitely hear it in industry. All of us hear it now, and that's the question that we keep getting, which is from upper management. And again, it's a fair question. Safely reduce the dig program. So can you perhaps give us some suggestions, some tips? How can integrity engineer go about maintaining the safety, but at the same time, is there any tricks to slim down the dig program and still achieve the same results, or get a better
Sure.
bang for the buck?
So a lot of this, here's my "it depends" t-shirt again, but it depends on what your dig cost is. So if you have a nice high dig cost, that's how I look at it, because it opens the door for an advanced assessment. So often digs are done. There's a safety margin for future growth, and so if we have a better understanding of that damage mechanism and whether it's growing. So for dense, a corrosion growth assessment, which can include, if we're worried about specific spots, I would include a look at the ILI, a like-to-like look at the ILI data to see whether we have signal growth, to look at all the corrosion pits to see whether there's growth across the board, or whether there's some outliers. So a corrosion growth assessment can help on the metal loss. Fatigue assessment helps on dents. Certainly, if you have a pipeline with low cycling, then a fatigue assessment can show long remaining lives, and that the dig program really isn't overly effective. And that can be, that's a pretty strong argument against, in certain cases, against not doing extra dent digs. The cracking anomalies are a little bit harder because there's a lot of uncertainty around it. So I do think you need to get out and do some crack digs to understand the data and to understand the anomalies you have on the line. As that builds up over time, then you're able to work on getting some of that conservativeness out of the assessments you're doing. But I think on cracks, it involves at least to start with investing in some digs. But in the other ones, it's understanding that there's drivers. It's going to take an anomaly, from the published size to the critical size, and whether that's the error band around the accuracy of the tool, well then let's drill down that, or whether it's around a growth mechanism, well, let's just challenge that assumption with a growth assessment to see whether that is warranted or not. So where the dig and the assessments tend to be, everybody's sort of cost structure can be quite different, but they tend to be cheaper than a dig. So, and you can assess multiple anomalies, and I think there's two ways of looking at that. One is it can prevent you from doing unnecessary digs, but the other one is it can give you a really strong rationale for doing the dig. So, if sometimes the question is, well, prove it, it's actually, yeah, just please prove it to me that I need to do it, and that can, show that that the dig is warranted and it's an effective, risk reduction method.
Yeah, I agree with that 100%. I find that usually in sort of good times, you're given more budget to do digs, and there's sort of a restriction on advanced assessments, like why do we need to do that? And then I would say I'd agree with you that this is probably an excellent moment to say, okay, we're being constrained on the dig side. Hey, remember those advanced assessments? Well, actually, you can whet the appetite by saying, if we go for these advanced assessments, we may have to do, it should lead to less digs, and then you can actually use that to your advantage to finally get the opportunity to do some of those advanced assessments. Let's move on to ILI technologies. There's a lot of so many vendors nowadays, so many different technologies. I think we all know the sort of the larger vendors, but if you could just walk us through the different technologies and what they're useful for and what they tell us. So for
Sure.
metal loss, crack likes, IMU, caliper, that kind of stuff.
Yeah. So let's start with metal loss. So the sort of the industry standard is magnetic flux leakage, called MFL tools. MFL is a mature technology. It's been around since the 60s. And one of the nice things about it is that once you have a magnetic field in the pipe, so they saturate the wall with these magnets, and then they measure the amounts of flux leakage. There isn't a lot of proprietary ability in getting that saturation, meaning that one ILI tool is basically doing what another one is for MFL. What matters is the number of sensors they have, how often they're measuring, how good are their data analysts, So they're relatively similar. The answers are going to be plus or minus 10%. It's looking for volumetric loss. In the common setup is axial, so it's looking at it in the direction we want. And so that's, and the assessment tools were really built around the data that comes out of MFL. So that's a nice mature technology. There are some nice increases in the number of sensors, and as electronics get, and the amount of sampling, and so the ability to see small pits is improving, but the basic spec is the same as it was, in the 90s. So the other way of seeing metal loss or common is ultrasonics. So ultrasonics require a liquid couplant, so used as sort of a niche tool by liquid operators. It's looking for a reflector so it can see laminations, and if you have some issue with manufacturing anomalies, it can be good in that. UT has the ability to be really accurate. So MFL is an indirect measurement. How much flux leakage can be correlated with what the depth is. Ultrasonics is an actual measurement of the reflector, so it's getting reflector off of the metal loss, and it can turn that into a distance and get a very accurate measurement. The sort of the downfall of UT is it needs that reflection, so if it has what's called echo loss or some kind of data dropout to the dirty pipe or something being off angle, it then can introduce some scatter, I think is the euphemistic term. So it's very accurate sort of until it's not. But you can do a more advanced metal loss assessment with the UT. So it's got some advantages, but it does have some trade-offs. So for dents, the most common is our geometry tools, geometry inspection. The most common is calipers. So they're just a physical caliper arm that is pulled normally in a combination tool. They can be run alone, but now they're generally run with an MFL tool, and they just measure the profile of the pipe. More sensor density is better. Some vendors are still running some of their older tools, and that's fine. I don't think it affects the accuracy a lot. It hampers you if you want to do an advanced assessment. So on dents, just make sure it's a high-res tool. So we're getting sort of 3, 4, 5 sensors per diameter inch. some people are using UT sensors to do geometry as well, where they use the standoff reading, and they're generally tied along with an ultrasonic tool or with an ultrasonic crack tool. And so that, my experience with that is it's roughly as effective as a caliper tool. So the geometry data is a little more robust too, so it's more consistent. And the technologies just aren't quite as complex. Cracking, of course, is the hardest one. There's shear wave ultrasonics. That's the tool that would have the best specs. So they need a liquid couplant, and they have a lot of sensors on them. The data is very complex. You don't get a report back in a matter of days. It's multiple months for the analyst to work through it. But it gathers the most data, and it has the best chance of characterizing and effectively sizing the crack and crack-like anomalies. It's not perfect. And then there are some other ways of going after cracks, and that's EMAT. So it's a contact ultrasonic shoe that puts a surface wave in, so it doesn't need a liquid couplant, it can be running gas. There's a couple EMAT tools out, and they're starting to show up in the smaller diameters as well. So that's really targeted at the gas market with smaller diameters, so we now have some options. And there's some success with using circumferential MFL tools to find cracking as well, because it's looking for volumetric loss. That crack does need to have a gap, and so if your cracks are tight, like SCC or a small crack under tension is not going to be open at all, then the circumferential MFL wouldn't find it. But if in the right application, it can be and is more effective at finding larger anomalies than smaller ones. So the good news out of it is that its bias is towards finding more severe ones than less severe ones. And people who have run crack programs and ended up with hundreds or thousands of digs, that's some operators actually like that and find that's a good way to grow the program, is start with a circumferential MFL and build up your database, because it's probably not going to send you on quite as many digs as let's say an ultrasonic shear wave tool. And then the last type is a XYZ profile tool. So that's included in most combination tools. So you get MFL sensors, caliper sensors, and then some accelerometers that are able to give the profile of the pipe. So that's helpful for finding things. So I think we all use it that way. If you have pipe movement due to slope instability or something along those permafrost issues, then you can do differential GPS, where you're comparing results from multiple runs to see if the pipe has moved or is creeping, and set some safe standards there. So yeah, that's there's a lot of vendors, so it can be a little bit intimidating. My advice on that is get a relationship with obviously a sales guy you like, but also with the data analyst, so that that you get to work with that department, because that'll really impact your results. So find a good fit there. And then there are a lot of new technologies out there, and back in the good old days, we would just go to the shows and walk the floors to see what was new, and some things are very static, and some things are changing pretty quickly. So
yeah, I always and I'm sure you would second this, I always would say that being on a first name basis with your analyst is like being on a first name basis with your banker or your accountant, right?
Yeah. They know a lot, and it can sometimes be a little hard to get it out of them. So it's just because of the nature of the job. Yeah, I definitely agree with that. There's a lot of if you don't know how to look at ILI data yourself or somebody directly on your team, then most ILI offices will sort of stand in and do that for you and do some interpretation of what they're seeing.
Thanks, Ian. Can you give us some advice in terms of, what do you see coming down the pipeline? What do you see in terms of the vision or the future of the industry in terms of assessment methods or technology? And where do you see us progressing to in the future?
Yeah, people are gathering a lot more data, and that's got some good sides and some bad sides. But that's really the challenge in front of us, is how to make sense of all this data. So an area where that works really well is doing advanced assessments with, as we know more about material properties of shapes of dents, and that really opens up some meaningful and helpful assessments to get us away from these old school rule of thumb approaches to pipeline integrity. So everywhere where that's happening, that's great. The Canadian regulators have built the ECA into the Z662, and that's recognized. In the States, PHMSA is moving towards an ECA as well. So that's fantastic, and that's a great use of data. The programs are becoming more structured, where the inspect, assess, determine what the reinspection interval is becoming more formalized, and that again is good. Gets really good strong process into pipeline integrity, and very auditable. You can get some certainty for your management as much as you can in terms of your program. All that data, though, it can also weigh you down and keep you from some of those important things, such as, does Joe, who's been here since 1973, know something about this dig? Or, he was there before, and it's like, yeah, we didn't, know something about it. Or, there's a crossing, and that pipeline, they don't always, their CP system can be screwy. So, there's some of these things you have to get out of your, get away from the computer, get out of the assessment, and go out and talk to people. And that was a skill that was much more prevalent when I started than it is now, because these assessments, they can talk you into thinking, it's because it gives you an answer, you can get talked into believing that answer is right. And then, it's not necessarily wrong. It's telling you something, but there's other factors that are sometimes don't show up in the assessment. So that's a piece that I think everybody needs to sort of take on themselves, and get to know the stakeholders around that pipeline, to see what else they can find out about the line to help them make decisions. Then maybe the last thing is dealing with that mountain of data that we're collecting. So the data needs to be working for you, not you working for the data. So I think it's important that I see a lot of people now just spending a lot of time moving spreadsheets around and cutting and pasting things, and that really pulls away from your analysis and getting at those things. So process is good, but I think a streamlining needs to be done fairly frequently. As you build up process, you got to sort of see where it's a bottleneck in you. People aren't getting to the work because it just takes them so long to get through every line now. So.
Well, thank you so much, Ian, for coming on. I know you're a busy guy. We've hit about the hour mark here. So again, thank you so much for coming on. If people want to reach out to you or contract your services, how can they reach you?
Sure. Probably the best way is email. My email is ian@idsmith-eng.com. So thanks for having me on the show. This has been a great conversation.
Yeah, I'll get my editors to use the magic of editing and get that on the screen underneath you there. And again, thank you so much. And thank you for coming on, and hope you enjoy the rest of the day.
Thank you, Hussain.
Take care. Hey everybody, welcome back. Hope you enjoyed that interview with Ian Smith. Please remember to like, subscribe, and share. And until next time, keep on pigging, digging, repair-a-coating, and backfilling. Take care.